That's kind. So, Daniel, Christina, Anton, and Daphne, thank you so much for organizing this program and giving me the opportunity to speak at this conference. And all of you, I have been watching with awe as I hear all of the science that's unfolding in your corners of the universe. The physicist in me knows pretty well that there are more things to, given the number of things there are to know, there will always be in any collection of humans, more humans who know more about most things than I do. But the human gets scared. And so now I'm a little nervous giving my talk. So I want to encourage the people in the room to pretend you're on Zoom and check email and, catch up with other fires in the world. So I'm less intimidated to speak. Huh?
And not ask questions.
Ask questions, it's okay. But when I look at you, you're looking somewhere else. I'm like, oh, okay, they're not listening. This is fine. So, good. So I will get started with what I want to do today. I thought I will partition my talk along the following lines. Proclamation. I'll give some big picture framing of the research track that we've been pursuing for the past 4 or 5 years. Some proselytization. I'm in love with optimal control and Cindy, so I'll tell you how awesome it is, and please everybody do it. And some ongoing work on active interfaces that I still don't understand, but I wanted to share with you, and some prognostication as to where we will go with all this stuff. So let's start with the big picture framing. This movie by David Rogers from Vanderbilt from 1957 is something we have all seen, and I have been fascinated with it since 2006 when I first saw it as Christina Marchetti's baby postdoc. And this is a more modern movie of the same cell where I'm visualizing actin and myosin. This is from the Betsig lab at Genelia Farms. And if I take a mechanical lens to what this movie is showing me, I would say that there is large contraction at the back end of the cell that is coming from the myosin activity. There is local extension at the front end of the cell that is coming from actin polymerization, and spatiotemporal regulation of these microscopic ingredients, namely actin and myosin, is giving rise to this dynamic and adaptive reorganization, which results in the function of directed motility. And so I thought to myself at some point, let me make myself one of these. So I want a bag of crap that goes where I want it to go. And that basically means I want materials with spatiotemporally programmable internal stress, so I can prescribe the forces that will be exerted by the active material in various points. And I want navigable motion. I want to understand how to architect the stress so that it goes where I want it to go. And I want this whole thing to be self-assembled. I put a few tens of different molecules in a cup, and this should happen. Okay, so that's the lofty goal. And we hatched a plan, and I'm going to give you the theorist version. And the plan was hatched with friends and family. For the purposes of this conversation, friends are people I share grants with. Family are people in my academic lineage, people who gave birth to me as a scientist or who listened to me thinking I will guide them, and the people who co-advise students. Okay, so this is a plot that involves a lot of friends and family. So my friends here have an active system which consists of roughly 3 ingredients. There is microtubules, length stabilized. There is a bundling agent, PRC1, that bundles microtubules antiparallelly. And there are motor proteins that walk on these microtubules. And the net effect of one of these units is that the microtubules slide apart. This is a time series snapshot that Zwanimir took maybe 10 years ago, where you can see the microtubules come together and slide, 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 and then fall apart. So that's my basic unit. And I want to put it in a bag. So I want to take a bunch of these microtubules and put it in a bag. And we have some bags in my family. This is a physical bag, a material bag, where it's a oil droplet. It's a double emulsion in which you're enclosing the droplet inside oil. And this is a system that Guillaume has already written a first paper on, where he was using this to study the Frederick's transition under confinement. And in my family, we also have another bag, which is an entropic bag, where I have a phase separating system of PEG and dextran. The microtubule likes dextran, and therefore the system phase separates into the microtubule sitting in the dextran phase, and now my bag is just the interface of these two phase separating fluids. And both Guillaume and Zwanimir have this bag now. So what we said was, I'll try to figure out the pattern of activity I need so that the bag exerts whatever force I want on the rest of the universe. I can't see how this can be wrong. We are not questioning Newton's law. There is something moving, so if I can prescribe the forces, it should go where I want it to go. And how hard can it be? So let's try. It turns out to be very hard, but we did a few things. The first step was to figure out the pattern of activity that I would need in order to make it do something. And this was work done by family members Saptarshi Ghosh, who's a graduate student getting ready to leave. I hope that he starts writing his thesis in a couple of months. And Mike Hagen, who I co-supervised the student with. And since I didn't know what we were doing, we started with a system that is very, very well studied at this point, the 2D active pneumatic, where you take this microtubule motor protein mixture that I described earlier and centrifuge it onto an oil-water interface so that you get a 2D film of these guys doing this ice cream churning dynamics, the 2D active pneumatic. And we have been studying the system since Zwanimir made it in 2012. And the theory for this system has been studied by all of us since Sriram made it up in 2002. So this is a very well-studied system at this point. It's described by hydrodynamic equations that you have already met a couple of times, and Tom walked you through it quite patiently. And I will quickly point out that what I have here is an active stress that is controlled by one parameter alpha that determines all of the non-equilibriumness of the phenomenology that I will observe. And it has kinematic terms, which is just telling what the flow induced by activity will do to the microtubules. And I have an energetic term which says how happy are the microtubules with whatever the flow is doing to them. And the energetic term is given by a Frank free energy. So this is the theory. And what I want to do with this theory is I want to be able to start in some arbitrary state of the system. This is some defective, turbulent state that the system is in. I want to figure out a pattern of this parameter alpha. I want a spatiotemporal pattern of this parameter alpha in such a way that the system ends up in some state I want. Maybe I want the pneumatic to be flat. Maybe I want the system to have coherent flow along some given direction. This is the question that we set ourselves. And the way we approach this problem is as follows. We use the technique of optimal control, but I will give you a physicist's formulation of what we are doing. The problem is the following. I have some nonlinear partial differential equations that involve these variables Q, the pneumatic order parameter, and the flow velocity U. And I have the alpha parameter sitting in my equation. And what I normally do, and what I would have done if I had Helena's data and I was trying to understand it, is there would be a fixed light pattern that somebody gave me, alpha of r comma t. There will be an initial condition for my fields, the Q alpha beta and flow, and I will solve the equation to get the flow field and the pneumatic order parameter at all later times. This is the classic initial value problem that we normally solve when we are doing physics. Now, what I want to do is I want to solve for alpha of r comma t in some time range. That's my control window, 0 to some time tf, given both the initial state and the final state of my fields. So what I need to do now is solve a boundary value problem in time. Okay? And this is something that people have thought about long and carefully in the field of optimal control. And the first question they ask themselves is this in principle possible? If I give you an initial state and I give you a final state and you can prove existence of alpha, that's called controllability. If you fix the initial state and ask what is the manifold of final states that are accessible given my initial state and the constraint of the dynamics of the system, that's called reachability. And in general, for a fully nonlinear system and something as messy as the equations that Sriram made up, you cannot prove anything, controllability or reachability or anything. But if you linearize those equations, then you can prove controllability. and in the linear dynamics, there is no difference between controllability and reachability. These are all just words because I don't want to show you nasty equations. Okay? So in the linearized system, you can prove that this system is controllable, but I want a bag of crap that goes wherever. So I'm going to take the proof of the pudding is the eating of it approach. Right? The physicist's approach. I don't care if the solution exists or not. If it numerically converges and I can implement it in the experiment, it exists. So what I write down is a cost function. The cost function basically says the system is happiest only when it is in the target state. The UTF and the QTF stand for the state in which I want the system to be in. And this cost function is minimum only when the system is in my target state. I add to it a few more things. Because I want to implement this in experiment, I know the range of alphas that the experiments can typically access. It's a very narrow range that they can move around in. So I put a constraint on the range of alphas that this system would wants to take. And I also penalize gradients in alpha because my digital light detector limits the gradient that I can set in my experimental system. So I penalize the gradients in alpha. Then I write down an action, which is this cost function and the normal Euler-Lagrange part of the action, where I'm introducing conjugate variables eta and nu that are such that they are basically acting as Lagrange multipliers that enforce the dynamics that I know my system obeys. Okay? Now I have an action. I'm a physicist. I can write Euler-Lagrange equations in my sleep. So I write down the Euler-Lagrange equations. Yes, Sriram.
Sorry, I'm really getting confused. Why is there an alpha of RT minus alpha squared term? I mean,
I just wanted the whatever solution my solver picks out to be close to the alpha twiddle so that it is close to the experimental range that this alpha can be in.
I see.
It's just limited by my experiments.
It's alpha tilde, right?
Alpha tilde, yes. It's a parameter. I just put a number in there to say, oh, this number should be close to 0.1 or something like that. I don't want it to give me solutions with 10 in there because my range is between 0.1 and something. Sorry, maybe bad notation. Okay. And so now I need to solve this. And to solve this, people have figured out efficient numerical methods that allow me to solve this set of Euler-Lagrange equations to get me the solution I'm looking for. These methods are partially described in this review and a bunch of other papers that are cited here. If you dig through them, you can find the numerical method. It's called direct adjoint looping. It's an iterative scheme to solve this problem. Okay? It's a technical detail. David.
So which member of your family can produce this exquisite control of alpha of R and T? So that's an activity that varies around in the fluid
Yes.
as a function of space and time.
Yes.
So how do they do that?
I will tell you in a minute.
Okay.
Yes.
I can wait.
In a minute. First, let me talk about my family, then I'll tell you about my friends. That can be done by my friends. So, in a minute. Okay? So, I just have an example solution here for you to look at. This is a solution where I'm aiming for getting coherent flow in the middle region of my sample. And the bottom panel shows the activity value that the optimal controller spits out. This is just a forward solution with that activity value so that I get coherent flow in the middle. And what I would like you to notice about the bottom region is that most of the light is outside the region where I want the coherent flow. Right? So under certain circumstances, the optimal controller produces a solution that is basically setting up vortices on either side of the region where I want the coherent flow so that I get effective shear flow in between. Right? So that's a cool solution that it produces. So in principle, I have a way to figure out what is the spatiotemporal pattern of alpha I need in order to produce a targeted flow state or a targeted nematic texture. The first couple of papers in this oeuvre have just been written by us. If you want to just see optimal control as a technique that is relevant for active matter, I recommend the former paper that deals with toner 2. That's where we did all of the math and understood what we were doing. The second paper deals with the active nematic. It's a lot more messy. It's not as pretty. The math is messy, the results are messy, and so on. The first one is in soft matter already, and this one is in review. Okay. Now, to answer David's question, my friends, Seth Freden and Zvonimir Dojic, decided to play the game of optogenetics. We know that there are all kinds of light-sensitive proteins in nature. So these plant proteins, that's called eyelid, that allows a flower to face the sun or the plant to bend towards the sun and things like that. You take this eyelid protein and attach it to the kinesin motor in such a way that the kinesin motor only acts as a motor when you turn on light and doesn't do anything when you don't shine light. So I can play the same game that Helena just showed us in her talk. I can have a digital light projector that will project different amounts of light in different regions of space in my system, and I can try to control what's happening. And these people implemented this closed loop control on the experimental system, doing some baby things like just using light patterns to control the speed of the system, using the light patterns to control the defect density of the system, things like that. Simple things, global things. They have already figured out. This paper is on archive, but it's being rewritten and we should update it and resubmit it soon, I'm told. Okay, this is friends. They will figure out how to do all of this. Now what I can do is I think I figured out what activity pattern I need to drive my system to where I want it to go. How do I figure out what this means in terms of light patterns in the experiment? If I tell them put alpha equal to 0.1 here and 0.2 there, they don't know what I mean, right? So I need to be able to tell them what light intensities they need in order to get there. So how do I figure that out? I figure that out by using SIMD and machine learning. So what is the game? I want to think about this system, the 2D active pneumatic. As I mentioned, this is a well-studied system that people have been thinking about for more than 10 years quite carefully. And so we know a number of things. What do we know to be true at this point? We can extract a length scale from these experiments. I can measure defect density and vortex size and properties like that. And these length scales, all of these guys are governed by a single length scale. And that length scale turns out to be some function of the ATP concentration. KSA is the acronym for the motor, so the motor concentration, and PRC1 is the bundler concentration. When I'm talking to my friends, what they tell me is I have millimolar of this and nanomolar of this other thing and so on, and then I have to figure out what those things actually mean. The theory says that that length scale should be set by square root of K over alpha. K is the pneumatic elasticity and alpha is the activity parameter. And from all of the measurements that a number of people have done, we have done it, the Barcelona group has done it, and Linda Hurst has done it. There are a number of measurements at this point, and everybody gets a different proportionality constant and things like that. There's some variability with respect to this. Proportionality is always true, the scaling is always true, but in terms of actually equating things, you can't quite do that. And similarly, we know that the time scales that I can measure in the system by measuring the speed of the fluid at various points and velocity correlation, autocorrelation time and things like that, I get one time scale. And this time scale is again a function of ATP, motor concentration and PRC1. And theory says that this time scale should be proportional to 1 over alpha. The proportionality constant is some number that we don't know and is variable depending on whose protein you're using and things like that, right? But the scaling is now robustly true. We've looked at enough data that now all of us agree that the scaling is true. Okay. Now, the proximate goal I want to set myself is to say I want to know what alpha is in my experimental system as a function of light intensity when I'm fixing all this other crap at particular values. Okay? So if I set myself that goal, what do I do to achieve that goal? The first thing, I'm actually kind of reordering this, the chronology to tell a better story, but let me just stick to this fake chronology. So the first thing to do would be to go from an experimental bright field movie like that to pneumatic director, defects, flow velocity, things like that. And my family member Mike Hagan and friend of the family Peng Yu Hong helped Chaitanya Joshi, a former student in my group, get started on this. Chaitanya has since graduated and works in the startup world. But basically what we did was the following. What I have is intensity as a function of x, y, and t. That's what I can extract as data from the movie. And what we have been doing, all of us, for many years now, is to say, intensity, as long as there is no photo-bleaching or some other drama like that, at some short enough length scale, it'll just be convected by whatever the local flow velocity is. So you use the intensity to back out the flow velocity by fitting on a short enough length scale. Or you know that the intensity change along the microtubule bundle is way weaker than the intensity change orthogonal to the microtubule bundle. So you measure the gradient in the intensity, cross it with the normal, that gives you the local director on a short enough length scale. And this is basically what we have been doing for many years now. But the same thing I could reformulate as a data problem, where I say that I have intensity at a time Tn at all my grid points, I have intensity at a time Tn plus 1 at all my grid points, and there's some matrix that relates these two. As long as my frame rate is high enough, this is the problem that I want to solve. And given all of the physical reasons that we just discussed, this is going to be a sparse matrix, mostly diagonal, going to have Jordan form properties, lots of nice pretty things. So then you go and tell your machine learning friends, tell me which neural network I should use given that this is the nature of the data I am looking at. They will give you a convoluted neural network or some other such thing to say, oh, this is the parallel scheme you want to use for this data structure. Then you just train it and figure out this matrix. So what we did was we built machine learning solutions that will allow me to take experimental data and convert it into director fields, convert it into flow velocities and things like that. It turns out that director field solution that we write down in this paper above is very finicky, and I wouldn't recommend it to you guys. Build your own. But the bottom one, the one with the optical flow, stop doing PIV. Optical flow is way better. Okay, so everybody switch to optical flow. It's very easy. Google has the primary algorithm out on their Google Brain website. Get it, then train it, validate it with PIV, you're set for life. So I recommend that to everybody. So what you can do is you can take a movie like this and produce flow velocities way faster than we could when we had to physically do the analysis, and there is a lot of, oh, what Gaussian blur are you choosing, what is the fit parameter, what is the fit range, all of these sensitivities were there. Yes, sir.
So basically you still do what you did before, but to generate the ground truth, and now this is just faster than the previous analysis based on taking gradient
yes,
images?
And also more robust to noise and things like that, where I don't have to worry so much. I don't have to throw out so much of my data when I'm trying to extract flow fields.
Okay, so you basically have some data set where you curate it so that, okay.
Yes. Good. Okay. Now, so now I have a movie, I can measure from it Q and V. Then what do? To measure alpha from the experiment, I take this data, I measure Q and V. I write down whatever the model is I think describes the dynamics of my system. For example, the active pneumatic theory that I showed you before. I compute both the left-hand side and the right-hand side of this equation from the data. And then I just do sparse regression to figure out those coefficients AI and B0 and B1 and so on. Alpha is one of those coefficients, right? This technique of being able to take data, postulate your PDE library, compute both sides from data and carry out sparse regression to find the coefficients is called SIND or PDE find. These are the applied mathematicians who figured all of the details out and wrote it up clearly enough that people like me could understand. So you just borrow and use your own thing to do it. So we did. And the first paper was published a while ago that had some results for non-optogenetic systems. But now we can run this on the optogenetic system and I can figure out what the value, the theoretical value of alpha is as a function of the light intensity in the experiment. So now I know what alpha light intensity translation is. So in principle, I should be able to just take my light pattern that I got from my optimal controller, convert it into intensity patterns, hand it to my experimentalist friend, and they will see whether it works or it doesn't work. I wanted to have closed the loop by now, but we haven't. We need a new digital light projector, which has been ordered from Israel, and we don't know when we will get it, and things like that. So I'm still not implemented in the experiment my dream of I will tell you the pattern and it will go where I tell it to go, right? But we'll get there. Okay. Now, I want to switch for the last 10 minutes or so and talk about something different, which is to say the other part of the problem, the bag. I'm going to put this active system inside a bag, and now I need to control what forces it exerts on the bag so that the bag is the one that's going to talk to the rest of the universe. Bag talking to the rest of the universe, I'm sure I can figure out because the rest of the universe is boring. It's some frictional substrate with contact interactions, or it is water, so I'm going to build a squirmer. We'll figure that out later. Let's now try to figure out the forces exerted by the active fluid inside the bag on the bag itself. And this is work done by my student Saransh Singhal and in collaboration with my friend Guillaume Duclos. And what we have so far is we have in the lab Bennett Sessa, a student in Guillaume's group, who is doing experiments in this phase-separated active fluid system. So I have bags of dextran that are holding the microtubules together. The entropic bag fluctuates because of activity in the PEG background. And I have a numerical model where I take the active pneumatic hydrodynamics equations that I've talked about so far, and I introduce a boundary. The boundary is given by that parameter capital X. The boundary just has no slip with whatever the fluid is doing at the site of the boundary. And the boundary stretching and bending exerts reaction forces on my fluid. And the boundary basically has a stretching cost and a bending cost. And you can play around with the stretching cost and bending cost to make it look as much as the experimental interface as you can. And you can solve the problem using immersed boundaries, so that what you have is you have an active fluid that moves, that deforms the interface generates some forces and remodels the active fluid. And you can watch this dynamics to see what happens. And what I'm having trouble with these movies for some reason, basically because this is the first time I'm using this slide. What we have now is we have both active droplets, namely the activity is inside and there is a passive fluid outside, and we have passive inclusions where there is a passive droplet sitting inside an active fluid. These images are the experiments, these images are the data, and in that experiment it's already been analyzed where you can see the blue regions are high curvature inside, red regions are high curvature outside and stuff like that, and you can measure these things using the video from the experiment. And I've had a lot of help from all of you guys in making progress on this project. This active interface, as I'm calling it, for me it's a bag. I want to understand it as a bag and how it deforms by the forces exerted by the active fluid. But that's not the only lens you can take to the problem. You can take to the problem a lens of phase separation and ask about arrested phase separation in the presence of activity. And there's some good insight that you have all given me on that using that lens. And there is the surface interface phenomena lens, where you think about propagating capillary waves at the interface due to activity. There's also a lens associated with wetting. You can think of the phenomenon as the active droplet wetting the passive environment, and that lens allows you to understand certain features of the fluctuations as we see them. And finally, there is also the lens of the active droplet, where you're thinking about how does the droplet deform and how does the droplet move when subject to the active fluid inside. So all of these things provide little pieces of the mathematical puzzle, and many, many more. And what we know so far, this is a result from friends and family. This paper from Christina Marchetti and Zvonimir Dojic tells us that flat interfaces are up-down asymmetric. A priori, them being up-down asymmetric is not all that surprising, because down is active, up is not active, but it's asymmetric in a very bizarre way. What you have is you have an overpopulation of large curvature fluctuations into the active fluid compared to out of the active fluid. So the passive fluid is poking into the active fluid apparently from the movie. Right? That's not what's happening. Active fluid is pulling the interface, but that's how it looks. So this is one feature that we know from the literature. And to add to this, what we also find is that not only is the fluctuation up-down asymmetric, it's also inside-out asymmetric. If you look at fluctuations of a droplet of the same size, so that the curvature of the interface is actually exactly the same, and you look at the fluctuations, they are different when the active fluid is inside and when the active fluid is outside. Now, and of course, this is experimental data that also shows the same feature. And the way that one can understand this is to build on, is basically outlined in Christina's paper. So this is my cartoon representation of the linear stability analysis that is there in the Marchetti, Dojek, and family members paper. So this is, I have a curved interface. The local curvature of the interface determines the alignment of the nematic at the interface. And if you imagine a sinusoidal deformation of the interface, and you think of a no-slip boundary condition on the active flow at the interface, what you will find is that in the absence of the interface, this bend deformation is going to set up this breaststroke vortices. That's the nature of a bend deformation. It will set up two breaststroke vortices. That no-slip boundary condition is going to kill the flow in such a way that the vortice's effective vortex is much smaller when you have a positive curvature. But when you have a negative curvature, that is a curvature in the other direction, the vortex is pointing the other way. You're not swimming into the wall, you're swimming away from the wall, right? And then the no-slip boundary condition, what it does is it effectively rotates the vortices, the direction in which the pushing force will occur. And this combination makes these fluctuations grow a lot more slowly compared to these fluctuations. And therefore you get these large deformations that poke into my active fluid. Now, this effect I also have, but I have another complication. The complication is confinement. In my active droplet in a passive fluid, the active fluid is confined, while in the passive droplet inside an active fluid, the active fluid is unconfined. So I have to unentangle the effects of confinement that give rise to additional features in my phenomenology. And we are in the process of sorting this out. I don't have a good plot yet, because the plot Saransh gave me, I don't quite believe right now. And the other thing that we are doing with this is we've realized that the curvature is a good metric for measuring active stress. I'm back on my bandwagon. I need to know alpha from the movie, right? And what we were trying to do is we're trying to measure the flow velocity on either side of the interface and thereby infer the shear stress, the fluid stress outside and the fluid stress inside. And if I know the curvature of my interface and thereby know its local normal, the force balance will tell me that if I take the stress outside minus stress inside, that should be the surface tension times the curvature fluctuation that I have, right? The stress outside is passive flow, the stress inside is active flow, and by just doing this analysis, I hope to get a statistical sense of what alpha is doing at the interface. Again, the experiments where we are measuring the flow velocity on both sides are just hot off the presses, and I don't have the analysis and a pretty picture to show you, but I am optimistic that we're going to get something nice out of this. So, what do I have so far? I'm out of time. I want to take one more minute. What do I have so far? I have a technique for spatiotemporally controlling active stress in my system. I have some understanding of how to work with bags. There's a lot more work to be done, and people like Petya will tell me how to put it inside GUVs and things like that, so I'm not worried about the bags so much. And what we're trying to do now is step up our game. We're building model-independent control, namely reinforcement learning, because what optimal control gives me is a coarse profile that can kind of get me to the system where I want it to be. But if I wanted it to stay there, optimal control sucks. To stay there, you're better off doing reinforcement learning. So we're building reinforcement learning to try to do the control better. And we're also applying the control theory to the interface so that I can program the shape change of the interface by controlling the alpha near the interface. But in all of this process, I will never forget the bag of crap that I'm going for, right? That's my mantra. How is this going to get me to my bag of crap? So I keep doing that. And finally, a rosy view of the future. All intellectual disciplines that are adjacent to us are going to help us a lot going forward. From a theorist's point of view, whenever I talk to my synthetic biology friends, and there are enough physicists working with synthetic biology that they can interpret what is happening there to us, and what they can do is they have an art of implementing bespoke, self-sustained biochemical cycles, right? I decide what reaction network I want, and I just implement it in a synthetic circuit. Right? That's awesome. So I can have reaction diffusion patterns that I want that will spatio-temporally modulate things and so on. De novo protein design. This is all in our minds right now because of the Nobel Prize, but even if you ignore that and you look at the things that they are able to do, we will pretty soon stop going around begging for purified proteins from every biologist who purifies a new protein and try to make it work with our system. We will look at their structure and make our own. And us, active matter people, we are sorting out the mechanics and the energetics. We understand the organization principles for intrinsic drives. We understand how things happen in space and time. Whenever you talk to these other people, they tell you something in some arbitrary high parameter space and some complicated chemistry and some various other things. But when it comes to our hands, we can say what will happen in space and time. So we are the people that will talk about the organization in space and time. And on the other side of the spectrum, it's astonishing how much we are learning from biochemistry and cell biology and organismal biology. And a number of you are working with real data from real experimental systems and giving me these nice paradigms that I can then borrow and mimic in whatever system I have access to. And of course, there is machine learning and data science sitting conveniently in between, which when used cleverly is awesome, right? And so I'm excited that you guys are all rowing the boat towards this ultimate goal of humanity. And I will be long dead, but I expect that we will be the people who will say that, oh, life just happens to be one active matter steady state that nature figured out. We'll make a lot more of that. Thank you for your attention.
Thank you. Let's start with the questions over there.
Yes, Rahul.
Yeah, for your, can you go on the slides where you have voids and patches?
Sure.
So in that study, how do you make sure that the boundary conditions are, the discontinuities in the boundary conditions are not an issue? For example, if you just arbitrarily cut a patch.
This, you mean the
previous,
far boundary?
No, the patch itself.
What is wrong with the patch?
No,
I just,
if you go to the previous image.
I'm trying to go. This one?
Yeah, this.
Yes.
Yeah. So if you arbitrarily cut a patch in like a state which is assuming that the velocity fields are continuous and such, how do you make sure that the patch that you have acquired from that process, its boundary are like does not have.
Okay, let me try to understand what you're saying. What is the patch I have cut? Just because there's a circle?
The interface, yeah.
Oh no, I haven't cut the patch. I physically put in a spherical interface that has a characteristic curvature and wants to be a sphere.
Okay, I misunderstood.
Then it is dynamically evolving under the forces that are exerted by the fluid.
Got it.
Does that make sense?
Yeah.
Yeah.
Thanks.
So, and the boundary conditions are no slip, momentum is conserved, everything is well behaved.
Beautiful talk. I'm curious, and I'm asking this as someone who doesn't know all that much about like machine learning.
Yes.
These algorithms that you have that learn how to control like flows in active pneumatics by like figuring out the right activity profile. Is there any way to extract like what it has learned about, say you want to do some operation to some local like coherent structure in the pneumatic. Let's say I have a -1/2 defect, I want to move it to the left. Can you tell that it learns, like, say I need to apply like a second order activity gradient or whatnot? Yes,
absolutely. So I don't know, I've only just started doing reinforcement learning, so there is no magical learning of control that has happened so far. The learning of control has been optimal control. But optimal control is gradient descent dynamics, Euler-Lagrange dynamics in landscape. So you can totally interpret everything that it spits out. And the interpretations in the context of, for example, the flattening the pneumatic is associated with shining light profiles just ahead of a +1/2 defect and just below the domain in which you want to keep the flat thing, so that the +1/2 defects get repelled out and the -1/2 defects are prevented from entering. So you can interpret it. There is value to interpretation, and you can ask, is it enforcing a second order gradient? Is the activity profile always parabolic in some regions and things like that? So those are all questions that you can ask. Once you get the control solution, you can analyze it and it gives you beautiful stories.
Thank you.
Yeah.
Yeah,
Yes, sir.
this is the perfect slide for this. So I didn't quite understand the argument why in one case sort of the boundary slows down the vortices and the other Okay, so it turns.
Yeah, so this cartoon is not really, you should read the linear stability analysis that Christina wrote down, but roughly speaking, let me go back.
So if it's the same argument as that, then I guess.
It's the same argument as that. It's just associated with, are you pushing into the boundary or are you pulling away from the boundary? When you're pushing into the boundary, this is the flow structure, and the no-slip boundary condition here effectively makes the strength of this flow smaller. And here, because you're pulling away from the boundary, the no-slip boundary condition on the wall just reorients the direction of the flow. It doesn't actually reduce the amount of flow from the activity for where this displacement is happening.
That's not how I interpret the math, but let's discuss this offline.
Yeah, sure. Everybody who likes the linear stability analysis never likes my vortex stories, but my vortex stories are true. Yes.
Okay, awesome talk. So my question is about the rest of the universe interacting with the bag, which you said is boring, and I understand it's boring from a mechanical perspective, but it could potentially be very interesting from a chemical perspective.
Oh, absolutely.
And so then how would you go about doing, if you had to do an optimal control kind of problem with respect to a non-trivial environment with whatever scalar field
yes.
and so on, like, you have...
Yeah, so I am right now hiding from that problem because there are other complications that I want to address first. But I would take the same optimal control approach that I have to the outside environment as well. Write down the mechanical properties of the outside environment and what is changing, and use that, write another action that will minimize for what you think the environment should be doing. So there'll be an action that has the active thing, and then there'll be an action that has the environment, and you'll have to minimize the combined action to get to where you want to go. So a very, very baby version of this is done in Suraj Shankar's paper with Maha and Vidya, PNAS from a couple of years ago. It's a baby version where they have done this, but you can do fancy things with it. It's only a question of finding a grad student willing to code up enough variables. So.
Thanks.
Yes, sir.
I can relate very much to your goal of trying to control active matter.
Yes.
But I guess my question is, why active pneumatics? I mean, we've seen many platforms of active solids, active fluids this week. So could you comment or give a perspective on, how to choose what the best platform is?
Any platform should work. The only thing I know how to do right now is optimal control, right? And for optimal control, all you need is a reasonable PDE description that has in it the control field. So if you have an active solid and you have a reasonable PDE description, like for example, I take an odd elasticity description a la Vincenzo, and there is some parameter in there which I can treat as the control parameter that I can change in space and time, then you can just set up optimal control and do your own thing for your own theory. So I don't think there's an ideal platform. I am just doing this because of friends and family. I should leverage my environment, right? So I'm nice to Seth and to Animate and Guillaume.
It's just like these active pneumatics look horribly chaotic. So
absolutely. So I'm stepping away from this active pneumatic. I have to be in the chaotic region because all of these, my friends have chaotic systems. But we are stepping away from active pneumatics and going to the 3D active suspension, where I have actually better frameworks to try to understand the fluctuations. And so, for example, the light bath that Helena had, where she could control the activity of the microtubules, of the E. coli. I can do that with microtubules and use that as a spatiotemporal bath that is driving something else. Those are the two things that I'm trying. But if you have data, or if you have an experimental system where you want to control something else and have a PDE description, I'm happy for me to write down the PDE and the Euler-Lagrange equations. That's the fun.
Thank you.
No, this is not the ideal system to do it. I'm just starting with a known devil. Known devils are always better than unknown angels.
Aparna.
Yes,
sir.
My optimal control friend.
Yes, and I should say, I've never said this before, but for a long time you've been my hero, and today you've definitely shown it. Sure, optimal control, I think, was the easy part. For me, the hard part of what you've done, and the thing that I thought was truly heroic, was going from alpha to I, so helping your experimentalist friends.
Yes.
What you've done right there is, truly more of a nightmare.
Bridge.
Your result was so simple. You just got a straight line.
Yes, that's because I showed you the pretty version of the data. There's all kinds of crap that happens when I go to high intensities, and at the very low intensities, I don't have enough resolution to be able to tell anything. So this is the pretty region.
S-shaped sigmoid, or?
I don't know yet, because that data is quite crappy and the postdoc is rerunning those experiments. But this is the region that I believe the curve I have.
But that's normal in experiments. You know, there's a region where, you know, you have sensitivity and regions where you don't.
Yes.
I mean, we have to deal with this all the time.
Yes.
But does this mean this nice linear, I mean, you're going through machine learning and PDE nastiness. And does it mean that this linear relationship means that there's some hope of simplification so that in the future you don't have to do all of this?
Well, that's what Seth claims, that we should be able to write some dynamical systems framework. We don't need this whole messy hydrodynamics, you're an idiot, and all of these things. But I haven't figured it out yet. I hold out hope, especially in Satwik's system, where he has actin sheets inside the 3D active fluid. It is possible that there is a much more lower dimensional representation which is amenable for control. I don't know that yet. I am hopeful.
Okay, cool. Thanks.
Okay, thanks. Yes, sir.
Yeah. So my learning. So thank you very much. One is I was impressed by the fact that it's the first time that it was the first talk using machine learning. In my community, this would be like
everybody
impossible, right? So, but now the second thing is that. Okay, the second thing is that one thing I would like to learn from you is the optimism.
Yes, active matter rocks.
Right. So it's yeah. So can I I sympathize a lot with the approach. This is exactly the viewpoint in which I'm trained. So you have a fluid and but actually you model the fluid. And now let me say the way I understand what you told us. So there are people that try to do control of Navier-Stokes equations.
Yes.
And they have a lot of problems, right? Okay, so part of it has to do with the inertia. Okay, let's forget about that.
Yes.
And now the thing is what you can do, right? So what is it that you can really control?
Mm-hmm.
And typically the problem there is that you only have access to boundary conditions, so you can prescribe flows at the boundary or forces, and you cannot act on the fluid directly.
Yes, yes.
So what I understand, I mean, okay, imagine that I can prescribe the force at will.
Yes.
Okay, then it's easy.
Yes.
Right? Because you prescribe any motion you want.
Yes.
And then from the equations, you get what is the force that is needed to...
Yes.
Right.
Yes.
Very well. And now there's the question of whether you can actually do that or not.
Yes.
And you are placing a lot of faith in Christina and Sriram, etc., and your own work.
Yes, yes.
And so essentially, it's a divergence of a field. So basically, you're saying, as long as I can prescribe this force field, I will be able to do. Okay.
Yes.
And now you say intensity of light.
Yes.
And now the question is, in these things, usually one does a balance of equations and unknowns, right? So how is it possible with a single scalar field to realize any vector field that is required to prescribe an arbitrary motion?
Right. So I probably cannot get to any vector field that I want. I'm limited by what my dynamics will allow. But my dynamics is controlled by one scalar, the alpha parameter. The one scalar is a complicated function of motor concentration, ATP, and PRC1. We have mapped out this phase diagram in various experiments that we have been doing over the years, where how this alpha depends on molecular concentration of these things. But it's one scalar. Now, if I fix all of those other things, that one scalar is a function of intensity is not that surprising. What is surprising is that I found some regime where it is reasonably well behaved and I don't have to worry too much about. And Jose basically outed me by saying, why is it so pretty? And it is not pretty in other regions. So I'm sure that I cannot do anything that I want. But I can do simple things. And simple things are enough for me to get my bag of crap moving, right? I just need to have directed forces and reorient the force in ways that I want. So I can do what I want to do. I cannot do everything. To do everything is what these model-independent control people are doing. You don't do reinforcement learning. You do some fancy multi-level LSTM forecaster or something like that and use that to do the control, then you have just way too many parameters that are there in your machine learning model, and it spits out some complicated thing you're supposed to do to the system. Then it's the cleverness of the experimentalist to predict how to do that in the system. And we don't know how to do most of those things yet.
Yeah. I don't know whether I should add maybe. So then this is really, it's a question of solving a direct problem and an inverse problem.
Yes.
So you're trying to solve an inverse problem.
Yes.
And typically you start by finding the domain of your map.
Direct problem, yes.
Right? So you have to first understand what is the space of reachable things.
Yes.
And maybe there's many, and only at that point optimal control becomes a choice between
yes.
equal alternatives.
I completely agree with you.
But you have to solve the direct problem first,
yes.
right?
Yes, I agree. There are a number of my friends and family in the audience who are working on solving the direct problem and figuring out what are the states that are accessible and things like that by using different alpha profiles, spatially controlled alpha profiles. And they have some good understanding of what alpha gradients do to the primary features of this chaotic fluid, which are the defects. And so there's some understanding, but I am just bulldozing my way to one goal, right? So this is an engineering problem now. The truth of it in generality at the moment, I don't care. I will get there. I'm too old to worry about that. I will die soon and I need to get my bag. Yes.
Thank you very much for your talk. I'm also an active control freak.
Nice.
So I was wondering, like, so you're using the active pneumatic, pneumatic hydrodynamic model, and I'm wondering how like accurate it is for long predictions. Because like in an experiment, when you're doing a deploy in your experimental system, you're hoping that the dynamics like you predict and
okay. So from what we have done, this is partly there in the paper, in both the machine learning paper, actually there's even another machine learning paper that I did inside, and in the Cindy paper. It's good enough for a given, if I start with a static initial profile of my defects and stuff like that, it's good for 2 defect length scales. When stuff moves up to 2 defect length scales, there is no problem. The theory predicts everything perfectly. Mm-hmm. And since I'm doing local control, that much predictive power is enough for me to get it to do what I want it to do. As long as I'm asking it to do simple things.
Okay. So I guess because you after 2 length scales, maybe your model, you'll
have to change the parameters. You have to change alpha or change background flow or something like that, because your model somehow is missing some of the fluctuations that happened.
Mm-hmm. And then you get a new control point.
Yes.
Okay, cool.
Yes.
Thank you very much.
Okay, last question.
Okay, thank you very much for your talk. So I have a question at the part where you define initial condition and the final condition, and you want to find the profile of alpha as a function of R and T, right? At that part, do you try machine learning? Because technically, if you have the dynamic equations, you can use backpropagation to find the weight of each alpha.
That's what the reinforcement learning and model independent control is about. Yeah. I didn't want to start with machine learning just because I'm very insecure about things I don't understand. So I wanted to start somewhere where I could see what was happening. That's why we did optimal control first. But we are doing exactly what you're suggesting. Saptarishi and one of Christina's postdocs, Aveg, are building the model independent control.
I see. So in that
and using backpropagation precisely.
Yeah, in that case, I have a further question, because in your cost function you define, you have A, B, and C, D as weight for each specific term, right? But they're all arbitrary. How do you define like which shape you want the most, like which arrow?
Absolutely. So this is a problem, and I chose the parameters because I had an objective in mind. I wanted the solution that will drive my system to some particular state. So I first guessed what strengths there should be. Then we moved around in the guess a little bit to try to see where we got well-behaved convergence, where the direct adjoint looping scheme converged quickly enough, right? And that was the thing that governed the choice. There was no actual thinking about the physical reasoning of these costs or anything else like that. It was just a game.
Okay, thank you.
Okay. Well, I'll take the advantage of being the chair of adding one last comment, because there was the question about different platforms.
Yes.
And as someone who works on active colloidal fluids, I would say that the pneumatics are great because you have this you know what the active stress is.
Yes.
And so the problem boils down to alpha, etc. But if you have a fluid that is driven by active particles like bacteria, we don't know what the active stress is, so it's a great problem probably for machine learning to solve, but thank you so much.